Hello, my name is Andrew Geary, and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. For this episode, I speak with Lynn Sykes about his new book, Plate Tectonics and Great Earthquakes, 50 Years of Earth-Shaking Events. Lynn and I discuss how the theory of plate tectonics transformed earth science and the petroleum industry, how earthquakes are more damaging in the central and eastern parts of the United States, the role Maurice Ewing played in plate tectonics in Lynn's career, and more. Lynn Sykes is Higgins Professor Emeritus of Earth and Environmental Sciences at Columbia University's Lamont-Doherty Earth Observatory. His application of earthquake science to monitoring underground explosions was crucial to treaties limiting nuclear testing. He is the author of Silencing the Bomb, One Scientist's Quest to Halt Nuclear Testing, and Plate Tectonics and Great Earthquakes, 50 Years of Earth-Shaking Events. For more information, read the show notes for this episode on your phone or at seg.org/podcast. Now, for our conversation. Before we explore your new book, I wanted to get your expert perspective on when I wrote this question, it was just the one earthquake, but now it's more recent earthquakes in California. You know, your chosen field has been seismology, which is the study of earthquakes. And in the 1980s, you served as chair of the U.S. National Earthquake Prediction Evaluation Council, a lot to say there, and that's something you discuss in the book. What were your first thoughts when you read the news on this event, and how do you see these earthquakes fitting into the larger story of future earthquakes in North America?
Well, this was one of the larger earthquakes in California in about 20 years, but we have been concerned on a time scale of 1 or 2 decades of larger earthquakes like that of 1906 San Francisco or 1857 in Southern California, earthquakes of about magnitude 8, which would make them great earthquakes. So, of course, now there is more concern that with the magnitude 7.1 earthquake, if it might lead to the triggering of yet larger earthquakes.
One of SEG's most celebrated and famous members, Maurice Ewing, plays a role throughout your book, as well as the story of plate tectonics. You write that Maurice was a skeptic of plate tectonics, as were you, until 1966. Why do you still remember the year that changed for you?
Well, it was probably the time that I did my most important scientific work, so of course I remember that. But you have to remember that in the 1950s and in the decades before that, almost all geologists and geophysicists in North America, both Canada and the US, thought that the continents were fixed. So Maurice Ewing was not alone in that opinion. I was told as an undergraduate at MIT that bright young scientists do not work on weird concepts like continental drift. So, of course, that led me not to think very much about it until I went to Fiji to work on deep earthquakes in 1965. While I was there, a colleague, Jim Dorman, told me about a paper that Tuzo Wilson of Toronto University had presented called Transform Faulting. When I got back from Fiji, I read that paper and I then thought about what could I do in seismology to try and prove or disprove Wilson's idea. Wilson's idea involved spreading along mid-ocean ridges like the Mid-Atlantic Ridge, but that spreading was interrupted by major faults that were then called fracture zones that intersected the ridge system. So it was those faults that Tuzo Wilson called transform faults. So when I got back to Lamont, I thought about that. So it was the most important thing for me was to make a decision to work on using seismology to either prove or disprove Wilson's ideas. In the spring of 1966, I was shown what was called the magic magnetic profile that Pittman and Hertzler worked on. Both of them were scientists at Lamont, Pittman and a graduate student still at that time. As soon as I saw that, I knew that spreading was likely going on and that I needed to try and work on Tuzo-Wilson's transform fault hypothesis. I started doing that the very next morning.
Why did you, speaking of Tuzo Wilson's paper, you mentioned in the book that you just knew you had to stop all your other scientific endeavors to focus on working on his hypothesis. Why were you so certain that you wanted to stop those other interests you had to focus on this idea?
Well, once I saw this magic magnetic profile, I knew that that was very important in terms of very large Earth processes, and that I had possibly the equipment and the data to do an important study that would show whether continental drift and seafloor spreading were occurring. So that was, of course, a very important thing and much bigger scale, and I thought importance than what I had worked on previously.
And you were correct on that. Your journey to publicly present your first findings on those items, the seafloor spreading, transform faulting, continental drift, had quite a few dead ends, false starts. Could you paint the scene for us of that bar that was hastily turned into a room suited for a scientific session at that San Francisco Hilton in 1966, where you first presented to the skeptic audience your findings?
Well, just before that, I had made a presentation of my first work on earthquake mechanisms and locations of earthquakes in the oceans. And I presented that at a meeting in New York City, a NASA facility. So there were a number of people there that heard that and were very excited about that. So I wanted to make a presentation at a major meeting, like either AGU or the Geological Society, and it was the GSA that was meeting quite soon after I made this presentation in October 1966. So I ended up as an additional speaker on a Saturday, in which my talk and several others were in the bar at the Hilton in San Francisco. There were skeptics there, but one of the most stimulating people for me was David Griggs from UCLA, who worked in rock mechanics. He came up to me afterwards and said, "That's great. That's just great." So that not only made my day, but it probably made my year or decade to hear that from him.
Speaking of AGU, let's move ahead to that in April 67 in DC, where you state that many of these, you state this was the birth of plate tectonics. What was it like to be a part of this conference where you were seeing these things finally being shown to be correct?
Oh, it was tremendously exciting. So we had not only continental drift, but seafloor spreading and transform faulting, in which I presented more work on that. But two of my colleagues from Lamont, Oliver and Isaacs, had worked on what happens at what are called island arcs, which we now call subduction zones, where one plate dips beneath another, as in the Pacific plate plunging beneath Japan, or the Pacific plate beneath the Aleutians. So they were able to show that plunging was going on, and seismology played a key role in seeing that seismic waves were propagated along that underthrust material to depths as great as 700 kilometers.
How did the understanding of plate tectonics become an integral aspect of oil and gas exploration?
Well, people in both the academic and oil and gas communities were interacting quite actively and knew about these results very quickly. The information spread really so quickly that plate tectonics was accepted by nearly everyone within 1 or 2 years, which is really astounding that it was so quickly. So, for example, several years later, Chevron, for one of their major anniversaries, invited Pittman and Maurice Ewing of Lamont and myself to a celebration in San Francisco, in which they said that plate tectonics was one of the most important things to affect their business in many decades and perhaps a century.
For maybe someone new to plate tectonics, maybe they're a student, just learning about this stuff. What is it about plate tectonics that is so important for people exploring for oil and gas?
Well, it sets the foundation in the same sense that Faraday's laws tell us how motors run. So plate tectonics set the scale, for example, in the South Atlantic for understanding how South America had moved apart from Africa within the last 125 million years. And the magnetic anomalies allowed us to trace how that had happened quite precisely. So that had a lot to do with the deposition of sediments and the formation of salt domes and the deposition of salt that led to salt dome formation. So great activity was focused on particularly the margins of Brazil and some countries and in Africa in terms of their petroleum potential.
5 giant earthquakes, meaning magnitude 8.5 or greater, have occurred from 2004 to 2013, more than any decade. What's your opinion on why that decade had so many giant earthquakes?
Well, we hadn't had very many for a long time. We have to go back to the 1950s to find a comparable period in which the Great Earthquake in the Aleutians in 1957 and other places happened within about 10 years. So we still don't understand why it is that we can have sequences of earthquakes that are quite removed from one another. It's probably just random occurrence that a number can occur within a decade of time. And then we have other periods of relatively few really big earthquakes.
Because that's almost reassuring there. You dedicate a chapter on earthquakes in the eastern and central US where you've lived and did most of your work there at Lamont. I know for me, I didn't give much thought to earthquakes in these parts of the US until I experienced the 2011 mineral earthquake while I was living in DC.
Right.
What is the level of seismic risk in these regions of the US?
Well, the number of earthquakes of a given size is quite a bit less than it is in, say, California. But the thing that is distinctive about earthquakes in the central and eastern United States is that they are felt to a much greater distance. So that makes an earthquake of magnitude 7.5, like that in Charleston, South Carolina in 1886, or the famous sequence in southeastern Missouri called the New Madrid earthquakes in 1811 and 1812, were felt to huge distances and made them much more damaging than an earthquake of similar size in California. Fortunately, they don't happen as often, but when they do, the effects on people and structures is very great.
During your early years at Lamont Geological Observatory, you talk about how one of the major contributions of Ewing and Jack Oliver, who's present throughout the book, were to be able to focus on topics that were ripe for really important research. And they believed you didn't have to be a genius to make an important discovery. For aspiring geoscientists out there, do you see a current group or scientists that if you were starting now, you would want to be part of what they're working on?
Well, in several places, there's excellent work going on. And in my field of seismology at Princeton, at MIT, Columbia, of course, my home institution, also Santa Cruz and Berkeley. The opportunities for studying seismology are much greater today than when I became a graduate student in 1960, and really about the only places at that time that were really good were Columbia, Caltech, and Berkeley. So I had a choice of where I went. Fortunately, I would not have done the work I did on plate tectonics if I had not gone to Columbia and Lamont.
And this kind of leads into this question. You've spent your life working on these challenging and meaningful scientific endeavors, but I was taken by something you write in how key the US Department of Defense's funding in the 50s was to your seismology field. And I've heard similar refrains from Sven Treitel and just kind of being at the right place at the right time, something he mentioned about MIT, among other things, and where you also attended as an undergrad. I'm curious right now if you see a particular area in the geosciences that if it had proper funding or had this infusion of money could possibly produce such a transformative discovery as plate tectonics?
Well, I think right now the combination of geophysics and geochemistry is very important. So I would favor places that have a mixture of people that work on areas that use information from both geophysics and geochemistry.
What thought or challenge would you like to leave the geophysics community on this topic of plate tectonics?
Well, I think to remember how important it's been that we went, at least in North America, believing that the continents couldn't move and that perhaps the oceans were as old, the ocean floor, as the age of the Earth. That turned out to be quite wrong. So we have a perspective then, just like evolution, that allows us to understand the Earth and many things like the exploration of petroleum much better.
What should I have asked you that I did not?
I think one of the important things that people don't ask me, and that was why did it take you so long to start working on continental drift? And of course, the answer there was that I had this feedback from faculty at MIT and elsewhere in the United States that this was not a topic worth working on. There is something similar to that today with what I would call long-term earthquake prediction, timescales of about 10 years, in which we cannot do prediction on that timescale or shorter yet. But there are a lot of people that believe that it is not worth working on, that it's for fools and charlatans. And I am working on this, and I am one of a small number of people doing this actively still today. But I think back to the comments made about continental drift, that they are rather similar to what a number of people have argued, that the earthquake process is very chaotic and therefore earthquake prediction is not possible. I was told that continental drift was not possible because the continents cannot plow through the old and strong material beneath the oceans. And that turned out not to be something that was happening, and yet continental drift was happening as well. So I think that there's similar things to be looked at with long-term prediction today.
Well, thank you for sitting down with me and speaking with me on your book. It's not only a story about plate tectonics, but it's also a journey of your scientific career, kind of told in a fascinating way to learn more about you, as well as all the scientific experiences and adventures you went on in your life and continue to do now, as you said. So thank you for your time and sharing a little bit about your work.
It's important to remember, too, with my book that I wrote it for an educated but general audience. So it's not a text in seismology or a strict rendering of plate tectonics, but it includes enough material so that people will become familiar with it.
Well, as a non-geophysicist or seismologist, I understood many parts of your book, so I think you succeeded in that endeavor.
Thanks a lot. Thanks again.
Please share this episode with a friend, colleague, or manager that would enjoy hearing this episode. Your recommendation is the single best action you can take on behalf of SEG's podcast. Go to our website at seg.org/podcast to find all our episodes and learn how you can subscribe for free directly on your phone. Original music by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Geary. The SEG podcast team is Jennifer Crockett, Allie McGinnis, and Mick Sweeney. Thank you for listening. This is Seismic Sound Off, signaling off.